All right, here we go. The value in dollars of a car t years from now is um, the function value of time. Um, value as a function of time is equal to 12,500 times 0.85 to the t power. So t being years. And question A says, what is the annual rate of depreciation? 1 plus r or 1 minus r if it's decay or depreciation. So A, hopefully we can see pretty easily, is going to be 15%. It's missing 0.15, and so it's going to be A is 15%, or as a decimal, 0.15, 0.15. All right, and then B, what is the annual rate of depreciation? So we're going to have that 6,000, because it says about what will in how many years will the value of the car be about half what it is now? So we want the value to be at 6,250. That's half of 12,000. So $6,250 is going to be equal to the original, the A sub naught, or the initial value. And so 12,500 times 0.85 to the t, and we need to solve for t. So we would divide each side by 12,500 and get that we have 0.5 equals 0.85 or 0.85 to the t power. But this is something we're going to need logarithms to solve. This would be log base 0.85, 0.85 of 0.5 is equal to t. But we're not quite there yet. We will be heading to logs very soon. But right now we're not quite there. So what would t be? So let's instead let's go ahead and come back to the original function and just graph it, solve it graphically. Graph it for right now. And so I've in my calculator here, where'd it go? There it is. In the calculator, we've got y equals 12,500 times 0.85 to the x power, to the t power. You can go ahead and graph it. And it was thinking it, but now it's not there. I can't find out where it is. So I'm going to have to be kind of smart. Well, it's first off, it's going to be up incredibly high because we're talking about 12,500. My window's right now set to 10. But I'm going to cheat a little bit and make it zoom to fit the graph. Sorry. Make it zoom to fit the graph. And it's going to think for a while. And now our x values look like they're pretty 1, 2, 3, 4. But our y values have been incredibly compressed. And so let's go through and we're going to use our trace function here. And we're just going to move along. So trace, and there's our little cursor. And so you may need to grab your calculator and actually do this along with me. I don't know if these numbers will be large enough to see. But we're going to just move along until we get the y value, the v of t value, equal to that 6,250, or as close as we can. And so I'm going to start just clicking along. Notice my y values are getting smaller. It's coming on down, and after a bit, our cursor is going to be kind of in the middle of our numbers, but we're going to have to just do the best we can. We're looking for the number closest to 6,250. So right now we're at 6,700, 6,400, 6,200 and something. That's probably the closest we're going to get. Looks like it. So 6,200 and something, but our x value, remember t is standing for, or x is standing for, we plugged in x instead of t, is standing for the number of years. So it looks like it's going to be right around 4.25 years, okay? Or 26 if you want to round that up. Oh, let's just round to the nearest 10. 4.3 years. So how long will it take? Well, we're going to kind of cheat. We're not going to use logarithms. We're going to say that it's going to be right around 4.3 years to get to 1/2 of the car's value. And we'll get closer as we go along and getting with the using logarithms to get our answer more specifically. But just as a point of note, if we bring back our graph, remember this, let's kind of move the trace function back out of the way. Remember that line is at 0. We're saying that it's 0 years. If we were able to go back in time, just look how expensive this car would get if we were able to get those prices all the way back up here. So these exponential growth and decay problems really do become really quite powerful because of that compounded growth and that compounded decay. And yeah, hope that helps.